right? In chapter 18, we're going to be talking about aqueous and ionic equilibrium. Now, you kind of get the theme by now. Chapter 16 is just what is equilibrium. Chapter 17 is going to be acid-base equilibrium. Now we're going to be learning about all types of aqueous ionic equilibrium. So that involves acid-base titrations, solubility with like the net ionic equations. Remember those from the precipitation reactions? There is actually an equilibrium associated with insoluble salts. When a salt is insoluble, remember we had silver chloride. That was one of the ones like silver, lead, and mercury chloride. Those are ones that were not soluble. Technically, they are. But we can consider them as kind of like a weak base or a weak acid or a weak electrolyte, where only a small percentage of the substance precipitate or is soluble. Very small percentage. And that percentage is denoted by a thing called KSP. And we're going to learn about that more in the next lecture, but just to introduce you to it, KSP. So that's an equilibrium constant having to do with solubility, but we'll get there when we get there. And today we're mostly going to be dealing with Ka and Kb and acid-base titrations, and buffers. So what's going on here? We'll start off with an example. Now, each year, I didn't know there was this many, but thousands of pets and wildlife species die of consuming antifreeze. Now, antifreeze, it contains ethylene glycol, which is very toxic, and because it can be metabolized to form glycolic acid. And this is glycolic acid. It's a weak acid, obviously, right? Because it's not hickel, hibber, hi, hino, hiklo, so. So it's a weak acid that is metabolized by your liver. And because it's a weak acid, even though it's weak, you still have this hydrogen would dissociate. And it would become H3O plus in your blood. That's not good. We don't want too much acid in your blood or too much base, because that can cause an imbalance. So maybe those of you who are into healthcare or maybe herbal supplements and into that kind of that, like, I don't want to say hippie stuff, but I mean, it has some real science to it, where you've heard of blood pH, and there's different people say drink alkaline water or whatever, just to regulate your blood pH level. But there's some science to that, because your blood pH level is held into balance with this buffer system. It's called the carbonic acid bicarbonate buffer system. And the buffer system, which I'll show on the next slide, it regulates the pH at 7.4. So your blood pH level is not exactly 7. It's kind of basic. So technically, you're all basic. Haha. And that level is 7.4. The reason why it's 7.4, we call this physiological pH. And the reason why that's beneficial is because that's where hemoglobin can operate the best. Hemoglobin's activity, which is hemoglobin's a protein that carries oxygen to all of your tissues. That protein has optimal activity at 7.4. If you have too much acid and too much base in your blood, it can throw off that pH balance, have an excess of hydrogen, and lead to acidosis. Or for too much base, alkalosis. And that's not good. That impedes your hemoglobin molecules from transferring oxygen to your blood, or to your tissues. Sorry. So it goes from your lungs, then there's the oxygen exchange, the gas exchange that goes on in your alveolar sacs in your lungs, and then that goes into your hemoglobin. Hemoglobin binds to oxygen. Hemoglobin gets transported into your different tissues and through your capillaries, and that will supply the oxygen for your body. So the idea is that this buffer system, or the buffer system that's on the next slide, this one, that's comprised of carbonic acid, which is another weak acid, and hydrogen carbonate, which is just HCO3 minus. And oh yes, ketoacidosis. That's exactly it. So if you would like that too much of a, like they have keto diet, right? It's not good. The science of that I can go into another time, but so acidosis, ketoacidosis, yeah, it's kind of the same thing. So this carbonic acid bicarbonate buffer system is regulated by a weak acid and its conjugate base. So remember we went over weak acid conjugate base pairs. And this is where this comes into play of what is a buffer in general. So in our body, we have the bicarbonate carbonic acid buffer system, where if we introduce acid, what's going to happen? Let's introduce an acid, HCl. We have a weak acid here, and we have a conjugate base. The conjugate base will then neutralize this strong acid, or whatever acid it is, it will neutralize it. And if you look at an equation, you'll have H2CO3 plus H2O yields H3O plus HCO3 minus. And this is an equilibrium. So let's say this is all fine and dandy. You have 100 molecules here and 100 molecules here. This is a buffer system. What will happen is if you introduce HCl, the reaction will go this way, because you'll introduce HCl, which will react with HCO3 to create more carbonic acid. And it will try to neutralize as much HCl as possible. If you introduce a base, like NaOH, the carbonic acid will neutralize the base until all the carbonic acid molecules run out. And this does change the pH of the solution a little bit, but not too much. This is why we call it a buffer. So a buffer's job is to, like this definition says, resist the change in pH by either neutralizing a weak or strong acid or base. It can do either or. So it's a very strong system for maintaining an equilibrium, especially in living things which have proteins that are optimal activity at certain pHs. And it's usually a fine balance. So blood pH level, you don't really want to get under 7.2 and or go above 7.6 or 7.8. And Brian, it's a really good question. What happens to the Na and the Cl left over? Now, we're going to be observing these spectator ions today, so maybe that rings a bell, that term. But these spectator ions, there are a lot of ions in our blood. There is potassium, there's sodium, there's some chlorine in there, there's copper, there's iron, there's a bunch. There's a lot of iron because that's conjugated in hemoglobin. But there's a lot of different ions, aqueous ions, that are not really important to buffer systems, but they are the carrier of some of these buffer system components. So it's a really, really good question. I'll talk about that more on the next slide. So now let's get into key definition. So what is a buffer system? I explained what it does, but what is it? So it either contains a significant amount of a weak acid and its conjugate base, or weak base and its conjugate acid. So it's either one of two things. How do you identify a buffer system? If it has a weak acid and its conjugate base, or a weak base and its conjugate acid. One of those two things. Okay. So how do you make one? There's two types of buffer systems, and they're made basically the same way. You have an acidic buffer system, which has the weak acid and its conjugate base. And then you have the basic buffer system, which is the weak base and its conjugate acid. For example, in this one where we have acetic acid as the weak acid, and we have the conjugate base, which is what we know is just acetate, right? The conjugate base for acetic acid is just acetate ion. But we can't have a solution of just acetate ion. It's tough we can't really make that. It's not really too easy to make. So normally we see it conjugated, to lack of better words, or kind of put together with another aqueous ion that will be our spectator, such as sodium or potassium or calcium or anything that's really soluble with acetate, which, because if you remember your solubility rules, acetate is soluble with every cation. Even if you put lead there, lead acetate is soluble. So we have these Na. So in the equations, you're going to ignore this Na. You're going to ignore it. And the kind of buffer that it looks like is going to be H in terms of equations, HC2, H3O2 plus goes in the water to make, I didn't leave enough room. Whatever. You're going to have H3O plus NaC2H3O2. And some of you might be like, wait, professor, that's not balanced because look, there's Na. But we don't care, honestly, because this Na, what's going to happen when this is put into our solution? This Na is drifting off and being an ion all by itself, as this picture shows. So this Na is not really going to contribute to neutralizing the acid or the base, whatever's added to this buffer system. We're mainly focusing on the changes that happen to the weak acid or its conjugate base, or vice versa, the base and the conjugate acid, when we're adding additional acids and bases to this buffer system. Okay, any questions on that? No? All right. So here's the equation for what happens if we add a base to this buffer system. So we're going to add some NaOH. I'll use a highlighter instead. We'll add some NaOH, and what's going to happen is the acidic, the weak acid that's in the buffer system, will neutralize some of the NaOH, and the NaOH will grab the hydrogen off of the weak acid. So before we get into what's happening, we know something about weak acids and weak bases. We know that they don't like to ionize, but they don't like to ionize by themselves. If we put acetate or sodium, if you put acetic acid in the solution with water, we know from our ice charts, from our Ka, that it's not really going to have much of a dissociation. And based on its Ka, which is very low, 10 to the negative 8th, or I think it's 10 to the negative 5th, still pretty low, you're not going to have that much ionization. But when you introduce additional base, which is craving hydrogens, remember, a base is a proton acceptor. When you add a base that's craving more hydrogens, the base is going to be like, oh, you're a weak base, or you're a weak acid, and you kind of cling on to this hydrogen a little bit more. Yeah, I don't care. I'm going to take that hydrogen away. And the weak acid will have no choice but to form its conjugate base. So what will happen is the hydrogen will be stripped off, and that'll create HOH, and that'll create water. And then the sodium, and this is kind of not really important to mention, but the sodium technically could go with the acetate ion here, but most importantly, it's basically Na plus the acetate ion alone, which is the conjugate base of acetic acid. And basically what happens if you there's a certain threshold of NaOH that this buffer system can withstand. If you have a little bit, the buffer won't change that much, or the pH won't change that much. But if you add a lot, more than the acetic acid could neutralize, then at that point, the pH of the buffer system will increase really, really dramatically. And that's where the buffer system gets destroyed. So any questions on how that works? We're going to be talking about that a lot today, of what happens if you go from one side to the other. And we're going to be talking about this with respect to equilibrium of acids and bases. No? Okay. So then on the other end of the spectrum, if a strong acid, or really any acid, is added to it, it's neutralized by the conjugate base component of the buffer. And the conjugate base, in this case, we dealt with acetic acid as our acid. The conjugate base will be acetate ion. So acetate ion will be here in the form of sodium acetate. And if you have a hydrochloric acid that's introduced to the solution, the acetate ion will be like, all right, I could use a hydrogen. The HCl will be like, I really don't want a hydrogen. I'm an acid. I want to get rid of it. So H will come off. The acetate will be like, oh, gimme. Because acetic acid is much more comfortable by itself as acetic acid than it is as an acetate ion, because it has a small Ka. And then you'll create this. And the conjugate base will go into its acid form. When you have a buildup of acid, of strong acid, you're going to end up with too much, or an excess, that the conjugate base of acetic acid cannot fully bind to everything. And then that excess will bring you to a very low pH, because you're going to have two acids in the solution. You'll have the acid formed by the neutralizing of the strong acid. You have the weak acid, and then you'll have the excess of HCl. So basically, another way you can look at it is a strong acid comes in to mitigate the change in pH. the solution takes that hydrogen and puts it onto a weak acid so that the hydrogen is kind of trapped. So it can't go free in solution. That's why buffer systems cannot be prepared with strong acids and strong bases, because they're so quick to dissociate. The free ions of hydrogen and hydroxide in the solution will always be high. No matter what you add to it, they'll just get higher. But we want to kind of quench those concentrations by sticking them to other ions, that being acetate or let's say if we had or creating acetate from it, or whatever, from the acetic acid. Okay, any questions on that? No? Okay. All right, so basic buffer system. Oh, sorry. Addition of a base. We kind of already talked about this already. If you have, basically what we're using is Le Chatelier's principle again. And because it is a equilibrium. Now, the best way to go about this is to do examples later on. But first we'll talk about, okay, conceptual question of what's a buffer. So buffer, remember, it's weak acid and conjugate base, or weak base conjugate acid. This one is a weak acid and a strong acid. Nope. This one's a strong acid, so automatically nope. This one is a weak acid and a salt. Nope. This one is a weak acid and its conjugate base. Now, because it has sodium, that doesn't matter. Think about the sodium. This is nitrite, sodium nitrite. In solution, remember, sodium comes off immediately and you have nitrate by itself. So even though the sodium is just a carrier, it carries the nitrite into the solution. Think about it as that. So then that would be your buffer system. Something we will talk about later on in the chapter is the common ion effect. So, and that is examined a little bit in going over buffer systems. But what it is in a buffer system, you're having two things that have common ions. For example, the buffer system we just saw of nitrous acid and sodium nitrite. You have the HNO2, which has a nitrite ion, and you have the NO2 free nitrite ion on the other side of the reaction. So this means that if you add another nitrite ion, the reaction will go to the left. So it'll kind of, based on the common ion that's on both sides, it will influence equilibrium. And this really takes precedence if we're talking about KSP, solubility with precipitation reactions, because you can selectively precipitate certain products from a soup of ions, depending on what is insoluble. And we'll talk about that more later on. But that's something that we can do with the common ion effect. And we have a question. So failing buffer system lactic acid buildup. That's different. So lactic acid buildup is caused from anaerobic respiration. So when you're, let's say you're doing a distance exercise, an endurance exercise, where you can breathe readily and get enough oxygen. Let's say you can run, let's say you're running 5 miles, right? You have enough, you're going at a slow enough pace and your body's going at a slow enough metabolism to where you can readily take in oxygen. And that oxygen can be transported to your muscles to go through aerobic respiration. Aerobic respiration does not create lactic acid. Anaerobic respiration does create lactic acid. That's where your muscles are oxygen depleted. So it doesn't necessarily have to do with the buffer system, but the product of lactic acid does decrease your blood pH level in your muscles, which that's what causes, well, that's part of what causes the cramps. Yeah. But the buildup of the lactic acid doesn't have to do with the buffer system. It has to do with the lack of oxygen and your body going into an anaerobic state. Very good question, though. Somewhat related, yeah. Okay, so finding the pH of a buffer, you can use an ice table. And instead of just going through what an ice table does, we're going to do some examples. Don't worry about examples. But we're going to introduce a new equation. I think someone mentioned it last week. Oh, we did meet last week. I forgot. Yeah, the Henderson-Hasselbeck equation. So the Henderson-Hasselbeck equation will be given on the exam, and it is very useful. It's a good tool to identify and calculate the pH of a buffer system, what we need is the pKa, the log of the base concentration of the conjugate base, and its conjugate acid or the combo, in essence. We need either the base and the conjugate acid or the acid and the conjugate base. We need the concentrations of those two, and we can put those into the Henderson-Hasselbeck equation to figure out the pH of that buffer system. So something else we can figure out is what happens if the base and the acid are the same concentration? Let's hear from you guys. What do you think? Based on the equation. Like, how would that affect the equation if they're the same? Good. Neutral, maybe not neutral, but pH equals pKa. That's the big thing. Now, because if you have a log of 1, that equals 0. So then you have pH equals pKa. That's very important because in the titration curve, we'll go over when you have the same amount of acid as you do conjugate base, or what that means is when the acid is halfway neutralized and half of it becomes conjugate base, that is when we have our halfway equivalence point. Now, that's going to be an important thing to know once we get into titrations. But also, that is when you have your most effective buffer system, when your base and your acid concentrations are identical, because then it can have the biggest buffer capacity, and it could neutralize either an acid or a base to the same extent. And another thing is, this can be most of the time, but this equation is used for when x is small, which in a lot of these questions is going to be too small, and you're going to have to consider it negligible a lot of the times. And here's the rule for it. So just look at the bold. You can read the rest on your own. But the initial acid and salt concentration, the salt meaning the conjugate, should be over 100 to 1,000 times larger than Ka. Now, Ka, for these weak acids, you're going to be seeing 10 to the negative fifth, 10 to the negative sixth. In those cases, they are going to, and when you're dealing with concentrations of 0.1 molar, even 0.05 molar, most of the time, it's going to be fine to use the Henderson-Hasselbeck equation for buffers. And keep in mind, it's only for buffers. What we can't do, and I see this mistake a lot, is where, let's say we're titrating acetic acid with NaOH. You can't put NaOH concentration in here because it's only for the conjugate pair that we can use the Henderson-Hasselbeck equation. All right, so let's do this question. So a buffer contains the weak acid HA and its conjugate base A minus, okay? The weak acid has a pKa of 4.82, and the buffer has a pH of 4.25. Which statement is true of the relative concentrations of the weak acid and the conjugate base? So I'll give you a second to look at it and look at the equation that I have pasted here. And what do you guys think? HA is larger. Yes. Okay, we have three answers. Good. Or two answers. Yeah, so HA is larger. Good. And the reason why. So we have our pKa is 4.82. So we can put that in the equation. Right on my pad. So pKa is 4.82. The pH, it goes down 4.25. This means we have to minimize this has to be negative. We have to make the log negative. And we know the log of 1 is 0. So the log of anything less than 1 is going to be less than 0. So in that case, acid has to be larger than base. So it would have to be A. Good. Any questions on that? Seems like you guys got that one. Good. All right. All right. So calculating the change in a buffer system, buffer solution. We can use stoichiometry. Now, one of the key things from Chem 1 is coming back, and that's stoichiometry. So we're going to have to be super aware of moles and of liters and of molarity. So if you don't like that, I definitely recommend you brush up on it. I have old videos from it. From those of you who weren't in my class, you can go see those. And those of you who are in my class, I expect you to remember it. That we're going to have a kind of different type of ice table for a lot of these questions when we're dealing with additions of different types of solutions. And what we're going to have is we're going to use the ice table the same way we always do. But instead of having it molarity, we're going to use it for moles, because the concentrations of them are always changing. If you add the concentration, let's say we do this. Let's say you have a traditional ice table. And this is why. I'll just show you why it works. If you have a traditional ice table and you have 0.4 molar, and then you have 0 and 0. If you're adding something to it, right? Let's say you're adding 0.2 molar of another thing. That changes the volume for the entire solution. Therefore, this 0.4 is no longer 0.4, but not based on the reaction happening, but based on just the volume change. So using molarity, when we're dealing with these addition of different substances with acids and bases, we cannot use molarity. We have to convert that based on the volume to moles. But for molar amounts, we can directly say we're adding this many moles, and then it neutralizes and we only end up with this many moles, etc. And then we can convert those moles back to concentrations, and those concentrations back to pHs. So I will give you a disclaimer. It's a pain in the ass a little bit. When you're doing the homework, you're going to beat your head over with the textbook. Yes, if you have a textbook. If not, I don't know. But it's not going to be too much fun. I think it's fun because I do this for a living, but you guys might just want to get through the assignments. It's kind of fun. It's like a puzzle almost, because you got to go, there's different steps to do. So I'll let you read that on your own, but let's do a question. All right. Now, for just calculating pH of an already established system, we don't have to use the molar amounts because we're not adding anything. Whenever we get to the second half of this lecture is going to be on titrations. Whenever we're doing titrations and we're adding substance, we have to use molar amounts or mole amounts. I'm not going to say molar amount. That's confusing. Mole amounts, physical amounts, because the concentration when you add something for everything automatically changes because the volume changes. So we'll just take it one example at a time. So calculate the pH of a buffer solution that has 0.1 molar H2 or HC2 or acetic acid and 0.1 molar of sodium acetate. And acetic acid's Ka is 1.8 times 10 to the -5. Okay, there's actually two ways to do it. The first way is you can do an ice chart, or with any buffer system, mostly any buffer system, you can use the Henderson-Hasselbeck equation. So we'll see it in action. pH equals pKa plus the log of the, here's a general term for the base. It's usually A minus times or divided by the concentration of the acid, which is HA. So this is going to equal the pKa, which is the negative log of 1.8 times 10 to the -5 plus the log of A, which is 0.10, divided by the log of the acid, which is also 0.1. So what's going to happen here? Log of 0.1 over 0.1 cancels out. And then we have, again, pH equals pKa. So all we need to do is solve for the pKa of acetic acid, which, can anyone help me out there? Nobody? Oh, we got an answer. Yay. 4.74. Looks good to me.
Isn't it supposed to be 1.8 times 10 to the -5?
Oh. I don't know what the negative. Sometimes that happens. -5. Yes.
Okay.
Yeah. Thank you. Sometimes when I'm typing, it deletes some. Yeah, I just did that again. It deletes a line. I don't know why it does that. But anyway, pH is going to be that. Any questions on that? That's a relatively easy one, but any questions on it? And if you want to do the ice chart, you can. So here's the solution for that. You're going to have just to show you, have your equation, which is going to be acetic acid plus the water, because you're putting it in water. And then you have H3O plus and your acetate ion. Remember, the sodium acetate goes away. The sodium part, we don't consider that part of the equation. Your initial is going to be 0.1 molar for each the conjugate base and the weak acid. And then you're going to have minus X plus X plus X. That will work into our normal expression for Ka. The X's will cancel out because the plus X and the minus X, because they're small, because our because our Ka is 10 to the negative fifth, and our concentrations are a lot higher than that. And then you could do the same math and end up with X, which you get as that. And then since you could do the negative log of X, yeah, basically negative log of that would be the hydrogen concentration. Negative log of that equals 4.74. All right, we got a question. So will some of the questions be easier to do with the equation than the ice chart? Yes, yes. So that equation is definitely easier to do with the equation, or that question is easier to do with the equation than the ice chart. That took us 2 minutes. The ice chart would have taken you maybe 3 or 4. So definitely. And in terms of vice versa, probably not. Henderson-Hasselbeck's pretty easy. There's some places where you can't use it, right? If it's not a buffer system, you can't use it. So for titrations, we can use it only sometimes, and I'll explain why. And Sebastian, you're right. So I added the Ka on the slides because I noticed before the lecture it wasn't there. But for the next example, it is there. But that's one you could easily look up, and they'll give it to you. You're never going to have to know a Ka value. All right, we'll do one more. So calculate the pH of a buffer solution containing 0.05 molar benzoic acid, which is that, and 0.15 sodium benzoate, which is just the conjugate base carried by a sodium. And you have benzoic acids Ka is that. So again, Henderson-Hasselbeck it up. Here we go. pH equals negative log of the Ka, 6.5 times 10 to the negative fifth, plus the log of the base concentration, which is going to be 0.15, divided by the acid concentration, 0.05. So that'll be the log of 3. And then that answer will be a certain number. I'll let you guys figure it out. 4.6. That looks right to me. 4.66. So on the homeworks, pHs normally to 3 sig figs. Yeah, I mean, if you have one that's like 10.2, you can do 3 or 4. 2 decimal points. We'll put it that way. 2 decimal points. Yeah. So also keep in mind, I always stress something, or I used to in Chem 1 more than now, smart calculations. Be smart. Does the answer make sense? If you're having a buffer system with a weak acid and its conjugate base, the pH should be a weak acid, somewhere between 3, maybe 2, the lowest, all the way up to 5 or 6. It shouldn't be 1. It shouldn't be negative. It shouldn't be 13. It should be somewhere in this range. So if you're struggling with that and maybe you don't know if you got the right answer, check the number. Does the number make sense? And here's how you do it with the ice chart. Same thing. And you get 4.66. Okay. All right. So here's just a pictorial representation of what happens if you add an acid or add a base to a buffer system and how it works. Basic buffers, same way, but you're going to have a weak base and the base is conjugate acid. And if you remember, this weird looking F thing from the previous slideshows is just an equilibrium double arrow. So it works the same way. If you add an acid to this basic buffer, what's going to happen is the base part will neutralize the acid coming in to create, in this case, ammonium anion or cation. If it goes the other way and you add a base to it, it will get neutralized by the ammonium ion into ammonia. So you have this whole system. Yes, the annotated slide. Yeah, okay. Okay, Sumi, that's a good All right. For that one, I'll definitely post the annotated slides because this F is really annoying. And you can't even, like, I tried. Maybe you guys think I'm lazy, but I tried. Look, I tried to, there's no way you can go in there manually. It says the equation was created with equation editor 3, which is no longer support. I never even heard of that. And you can't change it. So I tried. So I guess I could just write over them. Okay. Question. So a buffer contains equal amounts of a weak acid and its conjugate base at pH 5.25. Which would be reasonable value for a buffer pH after the addition of a small amount of acid? So what do you guys think? This is more speculative, but what do you think? You're adding a weak, or you're adding not a weak acid, a small amount of acid. So the pH go up, down by how much? And yes, we have B. B is the answer. So it'll go down by a little bit, right? So keep in mind, for pH, 1 unit is a lot. 1 unit means 10 times difference of the amount of hydrogen concentration. If you're adding a small amount of acid, it's not going to give you, in a buffer system, probably most of the conjugate base will neutralize that acid, and it will only create a small shift in pH because that conjugate base will now become the weak acid. So it'll make a small shift because you are introducing more hydrogen ions to that. And here's a better way to think about it. I just thought of this explanation. Let's say we have our sodium, we'll use sodium nitrite, right? This is a conjugate base of nitrous acid. When you add HCl, what's going to happen? Sodium, we know, goes away. The hydrogen will suck onto, or the NO2 will suck the hydrogen out of the hydrochloric acid, and the hydrochloric acid will dissociate automatically, and you'll have HNO2. That is not why the pH decreases. Because that doesn't add any H+, free H+ into the solution. The addition of the hydrochloric acid originally adds a crap ton of H+ into the solution. But because we have this conjugate base of a weak acid that can take on a hydrogen and hold it, what will happen is this weak acid that is now created from the hydrogen that is in there from the strong acid will only dissociate by 1%. And that 1%, that very small amount of ionization into H+, will cause a slight decrease in pH. And yes, you could think about it in terms of the equation. That's a really good way to think about it. Because that is molecularly the molecular action of what's happening here. It's very important to know and to make your life easier, is that what is causing the pH change? It's basically you're taking hydrogens from a strong acid that would normally be in the solution free, and you're transferring them onto a substance that can keep them on there for the most part. And that little trickle of dissociation that does come off of the HNO2 will account for a little bit of a pH change. But there's a point at which all of the NO2s have an H on them. And that's called the equivalence point. And we're going to learn about that in titrations, where any additional HCl will create a drastic change in pH. And that pH change will just correspond to the amount of HCl added because there's no more base to neutralize it. So definitely think about it in terms of the equation. It's easier to understand. Any questions on that? No? Okay. Okay, so we have two other traits of buffers. We have buffer capacity and buffer range. These are pretty easy, but buffer capacity is the amount of acid or base that a buffer can neutralize. And that's determined by, you can guess it, the amount of weak acid and conjugate base in the buffer. if you have more, then you're going to have a stronger buffer. And if you have a more concentrated one, you're going to have a stronger buffer. So the more stuff you have in terms of your buffer system components, the stronger your buffer is going to be. Then buffer range. So buffer range is the pH range at which a buffer can be effective. So anything above that pH range, it's not really gonna keep it in that range. So like it'll go haywire after that. And how do you figure that out? Is by using this rule that a buffer is the most effective when the base to acid or acid to base ratio is between 0.1 and 10. And if we convert that, just to cut to the chase, if we convert that, we come up with the buffer range as the lowest possible pH of the buffer would be the pKa of the weak acid minus 1, and the highest would be the pKa plus 1. So for acetic acid, we had a pKa of, I don't know, let's say it was 5.1 something. I don't know. That means the acetic acid acetate buffer system has an effective buffer range from 4.181 or 18 to 6.18. That's the effective buffer range. pKa plus or minus 1. Any questions on that? No? All right. So in buffer capacity, we talked about that already. If you have a concentrated buffer, obviously you're going to be able to neutralize more acid or more buffer, or more base than a dilute acid or buffer. Okay. A 1 liter buffer solution of 0.1 molar HF and 0.05 molar NaF, which action destroys the buffer? All right. So we have double the amount of the conjugate or the weak acid and half the amount of the conjugate base. So let's write an equation, just like Brian suggested. That's a smart thing. We'll write, I was writing numbers. Let's write the equation. HF plus H2O yields NaF plus H3O plus. And the Na, remember, it goes into the system, and the ether, it's just sitting there, whatever. All right, so we have 0.1 of our HF and 0.05 of our F minus, if you will, or our NaF. Let's see what happens. Adding 0.05 molar HCl. If we add 0.05 molar HCl, what's going to happen here? The F is going to try to neutralize it. And it will neutralize as much as it can, probably all of it, because the molar amount is the same, that many moles. We have 1 liter. So it will neutralize it completely, but then it won't be able to neutralize anything else. And it'll go completely over here, and it'll be very acidic. What happens with 0.05 molar NaOH? With 0.05 moles of NaOH adding to this system, we have 0.1 molar of the acid. That 0.1 molar will be able to neutralize it, and it'll be able to neutralize more. So it won't kill the buffer. Letter C, 0.05 of the NaF. If you add more of the NaF, that makes the buffer stronger, because what that'll do is then at that point, you'll have the same amount of HF that you do NaF, which will mean they're at the same concentration, which means the buffer is optimal. So what destroys the buffer? A, because it kind of depletes the activity of the conjugate base, which is NaF, the conjugate base's ability to neutralize any more acid, because that's the maximum that it can neutralize based on molar amount. Any questions on that? It sucks that A was the first answer, so there's no suspense to get to the right answer, but yeah. Okay, now let's talk about titrations. On acid-base titration, first of all, and it's going to be the second half of the lecture. What is it? An acid-base titration is when you have an unknown solution in an Erlenmeyer flask, like this. These are Erlenmeyer flasks on the bottom. You have a known concentration of solution in the burette. You are titrating. In other words, it's a funny, fancy word for just adding. You're titrating the acid in the Erlenmeyer flask with the base. So the unknown concentration is the titrant. The titrant is the acid most of the time. But let's just say the titrant is what you don't know. So titrant. And then the base, what you do know. Wait, hold on. They have it flipped. The titrant, take that back. They have it flipped. Okay, that's not correct, actually. So the titrant is normally, yeah, that's what I figured. The titrant is what you know. And then just the unknown solutions, we don't call it anything. We just call it the unknown solution. Now, what do they have? They have the titrant is slowly added to a solution of known. That's wrong. Normally, we add a solution of known concentration to a solution of unknown concentration until the reaction is complete. Technically, you can do either one, but traditionally, we add a known concentration to an unknown concentration because, well, we could do it either way. But normally, in a lab setting, you're going to have an unknown sample. Let's say you have an unknown acid sample, and your objective is to find the concentration of it. You're going to titrate it with a known base solution and add that in small amounts until the color changes. And the color doesn't change on its own. The color changes after you add an indicator solution. So an indicator solution, we'll learn about those later. You don't need to focus on them too much. It's basically a chemical that changes color when the pH is neutralized. So you put the indicator in first, then you start titrating. You start slowly adding the base. You get to a point at which the acid concentration is equal to the base concentration and it's neutralized. When it's neutralized, it changes color. And that's when you can stop. And then you can see, how much base did I use? I can use my mole calculations to figure out how many moles that was. Then that can tell me how many moles of acid there was. And then based on the volume, I can tell what the concentration is. Boom. Easy. So in a lab setting, it's pretty easy to do. You just have to do those stoichiometric calculations. Now let's do it on paper. So in a titration curve, which is going to be this, there's a lot going on. So what I'm going to do, I'll copy the titration curve. I'll put it here. So titration curve is the pH on the y-axis versus the amount of the titrant, meaning the amount of what's added. The inflection point is going to be where the equivalence point is. And what that means is where the acid is completely neutralized. Prior to the equivalent, this is really generalities, but you can see what happens as you're adding base, adding base, adding base. At first, the acid that's present will quench and neutralize all of the base until a certain point. That point, it will exponentially increase. And then the equivalence point, the inflection of that increase, represents the point at which the acid concentration was the same as the base concentration. In terms of in that solution, the molar amounts were equal. And then after that, the base will take precedence and control the pH level. And it will slow, if it's like NaOH, it'll slowly go up to 14. So any questions on how that works? Now, the pH at the equivalence point is not always 7. If you have a weak acid and a strong base, the pH of the equivalence point will be greater than 7. Because you're going to be dominated by a stronger base if you add more. And the vice versa is true. If you have a weak base and a strong acid, your pH is going to be, your equivalence pH is going to be lower than 7. But we'll see that firsthand. All right, so titrating a strong base with a strong acid, that's very simple to do and compared to the weak ones because we don't have to use the ice charts. But we can do an example of that. And basically, it's using our stoichiometry. And I'll show you an example. We'll do the example first, actually. Okay, so here's our example for that. So titration of a strong acid. These questions are clearly from the homework. And we'll do them together. So calculate the pH during the titration of 100 milliliters of 0.2 molar HCl with 0.4 molar NaOH. First, what is the initial pH before anything's added? Can anyone tell me how you do that? How do we do that?
Use the Henderson-Hasselbeck Equation.
I don't know about that, because is this a buffer? Think very simple. You could have done this in chapter 5. Before you add any NaOH, just basically asking you, what's the pH of this? 100 milliliters of 0.2 molar HCl. Anybody? Yep. Just take the concentration. Duh. Negative log it. Yep. You got it. You were all thinking of it. You were all thinking it, but I can tell you didn't answer because you thought it wouldn't be that simple, but it is. So what we can do is just take the negative log of 0.2. And that's your answer. And yes, Sebastian, it's already concentration. So the negative log of that, let me get my thing out, 0.2, and you get 0.70. Okay, that makes sense, right? It's hydrochloric acid. Remember, strong acid. For these strong acids, the complete dissociation. So you're going to have, in this original or initial solution, you're going to have 0.2 molar of hydrogen. That's automatically used in pH. But Sebastian's onto something. For the next ones, we do want to find the moles. So let's do that right now, because we're going to deal with neutralization. And first, we could also write the equation, HCl plus NaOH yields NaCl plus H2O. And I don't like to use red. It's too aggressive. I use blue. Okay, so we can figure out the moles. So 0.2 molar HCl equals X moles over 0.1 liters, right? Because molarity is moles divided by liters. Multiply those together, you get 0.02 moles of HCl. So that is the amount that we're trying to neutralize. All right. Next, what is the pH after 15.2 milliliters of NaOH are added? All right. So 15.2 milliliters of NaOH. What that means is we know it's 0.4 molar. So we could just find the moles. 0.4 molar equals X moles over 0.0152. And we can do multiplication, 0.4 times 0.0152, and that equals 0.00608 moles of NaOH. Now, what do we do with that information? Can anyone help me out? Remember, we're looking for pH. So we're looking for hydrogen concentration that is in the solution that is active, not neutralized. Anybody? Remember, they're neutralizing each other. So if you have this much HCl and we have only this much NaOH, basically it's asking you how much HCl is going to be left. That's not neutralized. Yep, Aman, you're right. Good. Subtract. Good. If you subtract those numbers, and I'll explain why you subtract in a minute, you get 0.002. You get, subtract those numbers, and you get 0.01392 moles of HCl left. Okay, So why that happens? And the question, I see you have a question. Some of you are not sure, but the reason why it happens is because you're neutralizing HCl with NaOH. If you have an amount, and it's in a 1-to-1 ratio. That's why we wrote the equation first. It's 1-to-1. It's not always 1-to-1, but in this case, it's 1-to-1. Most of the time, it's 1-to-1. That means for every mole of NaOH that you add, that corresponds to that many moles of HCl neutralized. It's basically asking you how many moles of HCl that aren't neutralized are left. So you subtract, that leaves you with 0.01392 moles. And then, Sebastian, thank you. The negative log of that would be the pH, 0.757. Does that make sense? And the answer is yes. It's larger than 0.7. And you only added a very small amount, 15 milliliters of NaOH to 100 milliliters of HCl. So it should go up by a little bit. Next, what happens if you add 50? So we're going to add 50 mils. So if you add 50 milliliters, we can just, here's what we can do. I'm going to erase this part. And keep in mind, these questions, it doesn't mean 50 milliliters more. It just means 50 milliliters. Oh, that makes sense more. Okay, yeah. Okay, so this answer, yeah, thank you, Sebastian. I was going to say, like, that answer seems too close to 0.7. So the actual answer is 0.9178, or you can just write 0.92. That's fine. That makes more sense. It shouldn't be that close, but okay. All right, we got it. So next, we can just say we're doing the same exact thing. We're starting out with 0.02 moles of HCl, but now instead of adding 15.2 mils, we're adding 50 mils. So we could do the exact same math. 0.5, that multiplied together, you get 0.02. I think. Right? Yeah, 0.02. So this means, and this is the amount of moles of NaOH that we're adding. We are adding the same amount of base that there is of acid. This means the net acid, if we subtract these two, it's 0. They're going to completely neutralize each other. What does this mean? The acid concentration is equal to the base concentration. Our pH is going to be 7. Because if you remember, H plus times OH concentration equals 10 to the negative 14. That's going to come back today. And if they're equal, then we have a pH of 7, and we have a pOH of 7 as well. So that's what happens when we neutralize. It's not 8. 7 is the neutral point. Okay, so there's no, okay, pKa only for weak things. This is a strong acid, strong base titration. There is no pKa's because we're not having partial dissociations. It's okay. Good question, because I'm sure because we were talking about that previously, maybe some people were confused. So I'm definitely glad you asked that. Okay. No, we're finding X. So you do 0.4 times 0.05. Okay. So let's move on to the next one where it says, what is the pH after 56.5 mils of NaOH are added? So we'll do the same exact math. And yes, it's easy. This is kind of straightforward for I don't want to say easy, but repetitive and straightforward for strong acid, strong base titrations. But when we get to weak acid and strong base, it gets a little bit more difficult. So let's just do the same math we did, but we're going to add 0.0565 mils. Do the same math, 0.4 times 0.0565, and we get 0.0226 moles of NaOH. Now, it's not going to be the same exact thing, but the same concepts apply. Can anyone explain to me what's going to happen here? Now we have more base than we have acid. So what do you think is going to go on? Feel free. You can open your mics too. Any ideas? Thank you, Christina. I think maybe the answer is 11.4, but any ideas? Oh, because is yours echoing? It's okay. It's okay. Anybody else? We have 38 students here. Anybody else have any ideas? Oh yeah, your roommate's in the class too. Maybe your roommate could mute themselves or mute me or like turn the sound off, and then you can do it, or vice versa. Or anybody else. There's 38 of us. You won't be on the video. Don't worry. Try to cut you out. I'm asking, so what's going to happen here? So okay. So aside, I'm going to say cut right here. That means, okay, the fact that no one's answering doesn't mean you don't understand it. I know you guys get it. At least most of you. That means you're not paying attention. So please, come on, be respectful, pay attention. I'm trying to do this. I'm trying to do this for you. So try to pay attention. But thank you for asking again what the question is. Participation is better than no participation. So I'm asking, now that we know from adding 56.5 mils of NaOH that we have a little bit more of NaOH than we have HCl, what does that mean? So, or how do we find the pH? What do we do from here? So what's your approach?
Would we just calculate it, the pH like normally, just with the new amount of moles?
Can you be more specific? So
find the concentration then.
So we started out with so the concentrations are both, we know them already. And we know the moles of HCl and we know the moles of NaOH, but we're adding the NaOH to the HCl. So first of all, what's going to happen here? Like, is this NaOH going to neutralize the HCl?
Yes.
Based on, yes, exactly. Based on amounts, right? So how much of the NaOH is required to neutralize the HCl?
0.02.
Exactly, 0.02. And how much do we have?
0.02.
More than that, right? So the excess is going to be the amount of NaOH that's not going to be neutralized by anything. It's going to be free. So that excess can be used to calculate not the pH, well, eventually the pH, but first the pOH, if you remember that one. And yeah, Christina, you're right. So does that make sense? Yeah. Okay. All right. So I'll just do the math. We have 0.0226 minus 0.02. That's going to equal 0.0026. Probably. Yeah. And yes, that's because NaOH is basic, right? So now we have, this is our net amount of moles of NaOH that's not neutralized. Excuse my handwriting. It's not neutralized. So now from that amount, we can do the negative log of it, or sorry, we can do the concentration. And then from there, we can determine the pH. So, oh, I think we did a mistake on here. Hold on. I'll do this one first. Now we can do the concentration because we want to do the concentration of the, so moles divided by liters. So our moles is 0.0026. Our liters of the entire solution is 100 plus 56.5. So 156.5, but it's going to be a point in front of it to make it liters. So what we're going to do is 0.0026 divided by 0.1565. That's going to equal 0.016 molar of the NaOH that's in excess. And based on that, we can solve for POH and pH. So the POH would be the negative log of that, 0.016. And then, wait. Yeah, so log of 0.016. 1.8 is going to be negative log of that. So then we do 14 minus 1.8. That's going to be 12.2. Oh, so I got 12.2 as the pH. Okay. Okay, so sorry, Christina. I thought 11.4 was the answer, but it sounded right. But after doing it, it's 12.2. Okay, so if you didn't follow me, what I did, right, yeah, so what I did is after you figured out the moles of excess NaOH, you need to convert that to molarity, to concentration. And the concentration is going to be the moles divided by the liters of the total solution. And you're right, that is a very annoying mistake. And I did it before over here. Now this pH, I don't think is the right answer for the first one, or for the second one, this 0.92, because we found that using the molar amount, I think we did the molar amount. I don't even think we did it correctly. So let's go back. Let's do this. Now understanding that, let's do this one again. I'll leave the answer up. So now we have 15.2 milliliters. And it's going to be 0.4 times 0.152. That's going to be 0.00608. I'll write that down. 0.00608 moles of NaOH. Subtract these two, we get 0.01. Hold on. 0.02 minus 0.0608. 0.01392 moles of HCl left. Now, dividing this number by the total volume. The total volume now is going to be 100. Can't believe I forgot this part. That just shows how exhausted I am. The total volume is going to be 100 plus 15.2, but in liters. So 115.2 liters divided by 0.1152 gives you 0.121 molar HCl. Then we take the negative log of that. Where's my log? Where'd it go? There we go. Log of 0.121 equals, oh, I got the same answer actually. Did we do it for the first one? I think, okay. 0.92. Maybe you did it. Yeah, okay. 0.92. Okay, so I think we did get it. Cool. Okay. With all that done, are there any questions? We'll do more, but are there any questions? I just wanted to do that because I don't think we did the concentration exactly. Random question. Calculator keeps rounding your answers. There might be a setting, but if it's rounding them to like 2 decimal places, that's fine. Yeah, the mode, scientific mode versus if it gives you like fractions, is like a fraction mode. Oh, maybe you could help her out with that, or sorry, him. I'm not sure, but you could help them out with that. Okay, that's a calculator issue. You guys got it. All right. Any other questions relating to this titration? We're gonna do another one. No? Okay. So now let's talk about titrating a weak acid with a strong base. This one's a little bit more complicated. But the key is, again, the top, this is pretty easy, but all we did wrong was, or all we tripped up on was converting the moles to molarity by using the final volume, right? But we want to make sure to do that. Now, titrating a weak acid with a strong base. Initially in the solution, and I'll walk you through this entire thing. We're going to do an example together, and then we're going to do one on our own. And make sure to take your time with these. On the homework, there's a bunch of them. Take your time, and you'll get really good at it. So first, you're titrating a weak acid with a strong base. Picture that the strong base is in the burette. You're slowly adding it to the weak acid. Initially, the pH of the weak acid is the pH of the weak acid, just like we did for weak acid equilibrium in chapter 16 or 17. So you do the ice chart and you find the answer for the pH of the solution, just for the acid. Done. Before the equivalence point, the solution's a buffer. You can use the Henderson-Hasselbeck equation. So in this part right here, the buffer range right here, we call it the buffer range because in that case, we have a mixture of both the acid and its conjugate base. We can use Henderson-Hasselbeck. Then we end up with the half neutralization point. That is where our buffer is optimal, meaning where the conjugate acid or the weak acid and the conjugate base concentrations are equal. In that case, pH equals pKa. And we can figure all this information out based on the amount of moles that are neutralized. After that, at the equivalence point, the moles of your acid equal the moles of the base added, not the conjugate base, the moles of the base added. So your half equivalence, and we'll go over this in the next example, but the half equivalence point is where the moles of your acid equal the moles of the conjugate base. The equivalence point is where the moles of the acid equal the moles of the base added, not the conjugate base. So then that would mean the solution would have only conjugate base in it. That means there's no more acid to be neutralized. So that means the original HA will now be all A minus, meaning the original acid, or weak acid, will be all conjugate base. And then we can do the moles of it divided by the liters to figure out the concentration. Then beyond the equivalence point, any excess OH is going to be used by, like we did before, to calculate the POH and then to calculate the pH from there. All right. So that's a lot of stuff. Let's do it step by step. There's two examples here. We're going to do the first one together. The second one you'll do on your own, and then we'll go over it together. And I'll give you 10 minutes, 15 minutes to do it because it takes a while. I want you to go slow. I don't want you to rush. All right. So what I'm going to do here is I'm going to make different slides so we have a lot of room to work. Oh, assuming I'm ahead of you. Okay. Thank you. Great minds think alike. Not saying I'm great, saying you're great. Oh, I guess that means I'm great too then. Okay, one at a time. All right, first one, calculate the pH. And the foolish ones never differ. Nice, I like that. I have the power to fail you, so don't forget that. No, I'm kidding, I won't do that. But that's a good joke. All right, so calculate the pH during the titration of 10 milliliters of 0.4 hypochlorous acid, which is HOCl, with 0.5 molar of NaOH. First, what is the initial pH before any NaOH is added? And the Ka is given. So we go right into basically asking us, what is the pH of this acid? So we do the ice table, the equation first, plus the water, the acid plus the water equals the H3O plus the base. Then our ice chart. Initial concentration of our acid is 0.4. And keep in mind, we can do concentrations here because there's nothing being added to it. Once we add stuff to this, this is the key difference between chapter 18 and 17 and 16. Before, for ice tables, we were strictly using concentrations. Now we have to use molar amount, moles, because we're adding stuff to it. I think there was one question like that on your chapter 17 homework, but most of it was where you're not adding anything. Now we're adding stuff. So when we add stuff, automatically switch everything to moles. So water, we don't count for anything. This is 0 and this is 0. Then we're going to subtract some amount of the acid because you know some of it is going to dissociate. And based on the value of Ka, which is 10 to the negative 8, that number is not going to be very high. So we can say X is negligible because the initial concentration of acid is 0.4. That's high enough. And then for the products, we have plus X and plus X. 0.4 minus X. Then we have X and X. Our expression for Ka is going to be X squared divided by 0.4 minus X equals our Ka. 3 times 10 to the negative 8. X is negligible because it's so small. And we can do multiplication. So we do X squared is going to equal 0.4 times 3 times 10 to the negative 8. And then the square root of that answer. So can anyone solve X for me? So I'm going to need your help on this one. So I want to be neat on the slides. So I'm going to need your help to give me the numerical answer. So work with this with me. Work through this with me. So I'm waiting for X. And with ding, 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 we have an answer. 1.095 times 10 to the negative 4th. That sounds right. I did this one before. Then what is going to, so that X is going to equal the conjugate base concentration, which is very small compared to the amount of acid that's there. Then it's going to equal the H3O plus concentration, which again, remember from chapter 17, can be directly used to solve for pH. So this X, we can do negative log of 1.095 times 10 to the negative 4th. And that's going to equal, what is that going to equal? .96. That makes sense. Awesome. All right. Before we move on, are there any questions on this? This is original or initial pH of a weak acid. Even though we went over it already on how to do it, is there any questions just so we know we're on the same page? It's okay to ask. We got a nope. Okay. If there are, you can come to office hours or ask me later. Next one. How many milliliters of NaOH are added to reach the equivalence point? Here's what I'll do. I will take the information and I will copy it here. Oh, we might need that Ka. There we go. Okay. So how many milliliters of NaOH are added to reach the equivalence point? The equivalence point, by definition, is when the NaOH concentration is going to equal the original concentration for the weak acid when it's completely neutralized. And remember, even though it's a weak acid, it still completely neutralizes by ionizing, by getting neutralized by the base, because the base is going to kind of rip that hydrogen off and facilitate the ionization and the neutralization. So the amount of NaOH, we know how many moles of hypochlorous acid we have. So let's figure out how many moles. So 0.4, I don't like red. We use green. So 0.4 molar, equals X amount of moles divided by 0.01 liters. This is of the hypochlorous acid. So that answer, I could figure this out on my own. I got this one. 0.004 moles of HOCl. So that's the amount of moles of HOCl that we have. Next, we want to see, well, we know because we're neutralizing it completely, we're asking about the equivalence point that we need. This corresponds to 0.004 moles of NaOH added. So that marks the equivalence point. Now, based on our given concentration for NaOH, which we know it's 0.5 molar, how many milliliters is that? That's all this question's asking, is how many milliliters does it take to completely neutralize this weak acid? So we would do, good, Sumi, good job. So it would be 0.004 divided by X liters equals 0.5 molarity for NaOH. And we can do multiply that over, divide that over. X equals 0.008 liters, which would equal 8 milliliters. Any questions on that? All right, chugging along. I'm going to bring some information with me. I'm going to bring, okay, we can remember the 0.04 moles. I'll bring this with me to the next one. And we'll put this, we're going to push it somewhere else, like SpongeBob. There. All right. Next, what is the pH after 2.2 mils of NaOH are added? Okay, so now we're adding some NaOH. Since we're adding something, we have to make an ice table with moles. So we can make an equation for it. Let's make the equation first, and then we'll plug it in. And we can write up here, we can write 0.004 moles of HOCl. We know that already. So we're going to have our HOCl plus water yields OCl minus plus H3O plus. Now, for these molar ice tables, we don't care about this amount. We care about the amount of acid and conjugate base. Because when you're adding a little bit amount of base, we can consider this to be a buffer system. And we're adding an amount to the buffer system because we're not at 8 yet. So keep in mind, anything that's before 8 is the buffer zone. And in that place, we can use, it basically acts as a buffer. So that's why it's important to find the equivalence point. So you know that any addition less than that would be a buffer system. And you can figure, even if it didn't ask for the equivalence point, you could still figure that out because you know a molarity for the NaOH, which is 0.5, and you know an amount. All right, so let's do the ice table for this. ICE. The initial amount of HOCl would be 0.004. Water, we don't care. This, we don't care. The change. We're adding NaOH, 0.2 or 2.2 mils. 2.2 mils is equal to how many moles? All right, we got to figure that out. So it's going to be 0.5 molarity divided by, or X moles. Oh, Sebastian, good question. So why are we crossing out H3O plus? Because we don't care about that right now. We can put that in there. We can put that in there, but we don't care about it because we only care about what's happening in the buffer system. If we have H3O plus, that's fine. But we don't need that right now. I know, Christina, we do need to convert to molarity at the end. But right now we can't because we have molar amounts. And since we're adding 2 mils, the molar amounts are going to, or the molar concentration are going to change. All right, so here we have 0.0022 liters. So now we're converting the NaOH amount, the 2.2 mils, to moles based on the concentration, and soon we got it. So that's thank you so much, 0.0011 moles of NaOH. This means that that amount of NaOH is going to be neutralized by the weak acid. So it's going to be minus 0.0011. Then you're going to have here, it's going to be 0. It's going to be 0 plus 0.0011. Okay. Now, if you're thinking into this really deeply, technically, the OCl minus is not 0. It is very small. And how small? We already figured that out. Initially, when this solution's made, your X is going to be 1 times 10 to the negative fourth. So technically, these answers are not perfectly this perfect. If they were, we'd have this initial concentration of being 1 times 10 to the negative fourth. And then we're adding this. But it's negligible enough that it doesn't really make that much of a difference when we're doing the ratios. So what we can do is we can do this math. We can do the subtraction there. So what is 0.004 minus 0.0011? That's going to be, I could do that, 0.0029. I don't know why I switched colors. That's how many moles we are end up with. Then the OCl minus would be 0.0011. Technically, it would be 1, 2. But again, we can make the 0. It's fine. Okay. Next, we know the amount of moles of both acid and conjugate base after this partial neutralization that's in the buffer zone before we get to the equivalence point. We can convert these to concentrations, and then we can use them in the Henderson-Hasselbeck equation to find the pH. So let's do that. The concentration of HOCl is going to be 0.0029 divided by the total volume now, right? It's not 10 mils. It started out as 10 mils, but now we're adding 2.2. So it's going to be 0.0122 liters. And what is that going to equal? Good. 0.238 molarity. Awesome. Then for the conjugate base, we have 0.0011 divided by our total liters, 0.0122, and that's going to equal what? .0902. And just to be clear, so if we put a 2 in here, if we made it 0.0012, what would the answer be? And Christina, yes. So it'd be 0.098. That's all right. That's the threshold. It's close. All right. So we're kind of flirting with it a little bit with neglecting this original amount of conjugate base, but it's tenfold different. It's more than tenfold different. It's about tenfold difference. So that's where you're okay. That's like the limit, the minimum of where you're okay. Normally it'll be more than that, or sorry, it'll be a lot less than that. It'll be 10 to the negative 7, 10 to the negative 8, but 10 to the negative 4 is kind of the threshold, especially when you're dealing with molar amounts that are in this range. Actually, wait a minute. I take that back. We're definitely okay because this is concentration, sorry, and these are moles. So we're definitely okay. I take that back. We're definitely in the realm of making the initial concentration of OCl minus negative or 0. We're okay. We're okay. All right. So this is going to be our molarity for our conjugate base. And Christina, to answer your question, yes, we can, but actually, well, yes, we can, but we're not going to. Because if you get good at it, you can, but we want to go through every step like we should. We want to follow the equations, but that's a good thought. You can do that if you want. Okay, so let's do the Henderson-Hasselbeck. So pH equals pKa. pKa we don't have, but we have the Ka. So we have the negative log of the Ka, which is 3 times 10 to the negative 8, plus the log of the base, the conjugate base, which is 0.0902 divided by the concentration of the conjugate, or sorry, of the weak acid, 0.238. And what does that equal for someone that can give that to me? That would be nice. Any answers for that? For the pH? $7.1. Maybe. Sounds good to me. 7.99. Oh, that's too high. 7.1. We'll go with 7.1. Okay, so 7.1. All right, it's not a very good buffer. Well. Oh, wait, that makes sense. Well, it's only 10 mils. And it's more concentrated. So I guess that makes sense. We're almost there already. Okay. Yeah, actually, that makes sense. All right. So then what is the pH after 22? Oh, we're going to drag our information. So what is the pH after 22.8 mils of NaOH are added? So now we are above the equivalence point. So what does this mean? This means that the equivalence point we calculated happens at 8 mils. 8 milliliters of NaOH equals equivalence point. This means that any milliliter amount over 8 will correspond to our pH by the concentration of OH. So what this means is that 22.8 minus 8 is going to be 14.8 milliliters of 0.5 molar NaOH. That's where we're adding. Oh, how do we know it's the equivalence point? Because we know that we have 0.04 moles of the acid. In order to have equivalence point where they're both equal, the added base to that acid, they have to be equal concentrations. So we calculated how many milliliters of our base is required to get that amount, the same amount as there is for acid. You're welcome. Okay, so now we know the excess will be 14.8 mils. So now we can figure out how many moles of NaOH is 14.8 mils, and then we can put this into our equations, and we can rationalize it out. So we can do 0.5 molar equals X moles divided by 0.0148 liters, and we can calculate our moles. X is going to equal, what is X going to equal? (7.4 10 to the negative third moles. And this is going to be All right, so that's going to be the moles of NaOH that is in excess. So now we can use the amount of, or the molarity of the NaOH directly to figure out the pH. And then from that, we can do our new 7.4 times 10 to the negative third divided by our new volume. So our new volume is going to be our 10 mil. Oh, it's on this page too. Our 10 mils plus the 22.8 mils. So that's going to be 32.8. That's going to be 0.0328 liters. And what will that equal? .2256. Now, this is the moles of OH that's free in solution after the neutralization occurs. So now from that, we can figure out the negative log of that, which would give us the POH, not the pH, because we're doing negative log of NaOH, a strong base that would all dissociate into OH minus. So negative log of this is going to equal what? 0.2256. Negative log of that's going to equal 0.6. That makes sense. 0.6466. And that's going to be the POH. Then 14 minus the POH is going to equal the pH. So that's going to be 13.36. Yeah, 3.5. Same thing. Okay, good. So that's the pH. And that makes sense. Think about it. You're adding double the amount of strong base, and that is more highly concentrated. So you are obliterating this buffer system. You're adding way too much. And that makes sense that the pH is around 14. Okay. So any questions on that? I know it was pretty strenuous and there's a lot going on, but any questions on it? And I will post videos going over more of these problems. None for right now? Oh, okay. All right. Good. So good. So I will, yeah, definitely need practice probably. I understand that. Oh yeah, I'll go back. This slide. Okay, so now something else I could ask here is, there was another question. There was what is the pH at the equivalence point? We can find that out too. So here's the equivalence point, is how many mils that it took to get there. It took 8 mils. Now, what is the pH at the equivalence point? That's what we can figure out. So for that, it's not going to be 7, because you're going to have a strong base. It's going to be above 7 because you have a strong base and a weak acid. So you can graphically, it'll look like this, where you have, this is going to be like 3, this is 7. So it's going to be around like 8-ish. If that makes sense, like that. It's going to be somewhere around like 8. Okay, so how do we figure this out? What we can do is use our molar amounts, and we can say that here's what we'll do. We'll erase this. So here's actually this is actually a little bit complicated. So we know that we need 0.04 moles of NaOH. That's in 8 mils. Sure. Okay. So now let's write an ice chart. Write that plus H2O yields the OCl minus, which is the conjugate base, plus the H3O plus. All right. So our initial 0.004. Our initial here is 0, initial here is 0, initial here, whatever. Ice. So if we're neutralizing this completely and getting to the equivalence point, our change is minus 0.004. That means all of the weak acid becomes its conjugate base in moles. And then we have this, but whatever. Then this will be 0. This will be 0.004. And we don't have to worry about this right now because this can't directly tell us the pH because, well, we'll see if it can. I'm not sure in this case. I think it varies, but don't worry about this. Here's the way to do it. So you have your moles. This is the amount of moles of conjugate base. Now, keep this in mind, is that because this is a conjugate base, it also has not a dissociation, but an association rate in which you can find the pH from. So what we can do with this is find the molarity first. The molarity is 0.004. And I'm not sure if they're going to ask you this kind of question, but it's good to know about it. 0.004 divided by the volume. Now the volume changed. It was originally 10. Now it's 18 because we added the amount of NaOH required for the equivalence point. 0.018 liters. And it's going to be moles. So the concentration of our OCl minus is going to be 0.22 molar. Okay. So now from this 0.22 molar, we could do another ice chart. I know this is a pain in the ass, but we could do another ice chart. And this will dissociate or reassociate into HOCl plus H2O. Or we can say OH minus. Well, hold on. Yeah, OH minus. This is going to be plus water. The H is going to go here. You're going to make OH minus because it's a base. So then on the bottom, we can have the OCl minus is going to be 0.22. This is going to be 0. This is going to be 0. Then we can have the change is going to be minus X plus X plus X. 0.22 minus X, X, and X. Then we have X squared over 0.22 minus X equals, now, instead of Ka, we're going to use Kb. For every Ka value for a weak acid, the conjugate base has a Kb value. That Kb value can be found from 10 to the negative 14 divided by Ka. So I know that's a lot. I think there is one question like that on the homework, but are there any questions about what I just did and what to do? This is at the equivalence point. And if you're confused, this is actually, these notes are written in the slides of what to do. No questions? Okay. I find that hard to believe, but all right. Okay, so 10 to the negative 14 divided by the Ka. Let's see. 3 negative 8. I got 3.3 times 10 to the negative 7. That's going to be Kb. So then in this case, the X can cancel out and we do the math. So we multiply the 3.3 times 10 to the negative 7 times 0.22. I know I'm running out of space. Times 0.22. And then we take the square root of that. So that would be the square root of 7.3 times 10 to the negative 8. Hold on one second. And we get, oh, I just clicked the wrong button. And we get for X 7 point, doesn't make any sense. 7.13. Wait. I think I did that wrong. Hold on. Let me do that one more time. So I did a log of it. That's why. Square root of 3.3 times 10 to the negative 7 times 0.22. And that makes sense. So that means we're going to have X is going to equal 2.7 times 10 to the negative 4. Now that is, I know it's a lot, but 2.7 times 10 to the negative 4. The molarity. That is going to be our OH concentration, which we can put in our POH and then find our OH, or find our pH. So we can do negative log of that. Now I'm going a little bit faster because we've seen this math before. 10 to the negative 4th. And then we do 14 minus 3.56. Which equals 10.4. So that's high, but that makes sense because the acetic acid is a pretty weak acid to begin with. Okay, so I know it's a lot. But now, what I'm going to ask you guys is to try this one on your own. So, and then we're almost done. We're not going to go for too much longer. We'll do some conceptual questions, and then we'll end pretty soon. And then we'll do solubility next week. So for this one, it says find the pH at each of the following points in the titration of a 25 milliliter of 0.3 molar HF. So hint, hint, find the moles immediately. With 0.3 molar NaOH, the Ka value for this weak acid, or sorry, of HF is 6.6 10 to negative 4. So you're going to do initial pH after 10 milliliters, after 12.5, 25, and 26. So I'll give you 10 minutes for that, or 15. I'll give you 15 minutes until 8:20. And if you have any questions, you can vocalize going over titration curves. Now we have these two titration curves. They're of 25 milliliter samples of unknown monoprotic acid, right? And monoprotic means it has one proton. And there's A and B, and they're both titrated with 0.1 molar of NaOH. The titration curve for each acid is shown below. Which is more concentrated? So what do you guys think? The concentration for the acid means that wouldn't it take more base to neutralize it if it's more concentrated, right? There's more molecules. So which one of these represents one with more molecules of acid? Good, A, right. So acid A, because it takes 30 milliliters to start to really get out of the buffer zone. Here, only 20 milliliters, and we start to get out of the buffer zone, and we start to neutralize everything. Good. Next is which of the two weak acids has the larger Ka? So keep in mind, larger Ka is going to be the dissociation, or the product over reactant. The larger the Ka, the stronger the acid. Oh, the blue boxes. So the blue boxes, they actually show I don't know. I covered them because they actually show the answers. But they show the wrong answer. They show wrong information. I don't know why. I'll show you in a minute. But let's figure this out first. So if the acid, which one of these has a higher Ka, meaning a stronger acid? Yes, acid B. And it's, yeah, exactly. It starts at a lower pH. Therefore, you're going to have more at this initial point. You're going to have more of the A minus that's there. And that's the answer. But look, here's what's underneath. So this is wrong. It's not more concentrated. This one's more concentrated, but this one's stronger. So it just, and the thing is, I couldn't remove it. It's part of the picture. So the only option I had was to do that. I mean, I could have made them white, but whatever. That's where these slides are at. Like, They have a copyright thing at the bottom, but who's stealing this stuff? Honestly, it's not that good. Okay, so we'll end with. Don't worry about that. All right, so we'll end with polyprotic acids. We're not going to really focus too much on them, but there's two equivalence points. One is for a strong acid because you have the first proton if it's a strong acid. Well, in this case, sulfurous acid is weak, and it has two weak acid strong base associate or equivalence points. But don't worry, we're not going to cover questions involved with those calculations. If they are, they're going to be simple. We can cover it. Don't worry about that too much. Monitoring pH during titrations, you can use a pH meter. That's the easiest way to do it if you were in a lab. And phenolphthalein is an indicator. Don't go crazy with the indicators. That's just the main one that around pH 7 or 8, it starts to change color. There's methyl red. Yeah, if you use it in lab and you go to lab, then you use that. Methyl red is another one that has different colors at different concentrations, but phenolphthalein is the main one. And then for next week, we'll start at solubility equilibrium, which will focus on it's easier than the acid-base stuff. We'll put it that way. It's the solubility of the insoluble things that we thought were insoluble before, but actually have a rate of dissociation or have a solubility product, which like silver chloride, which you thought was insoluble in Chem 1, it's soluble, but to a very low degree. Titrations with copper. Well, copper is going to be blue in solution. So you have, that'd be fun. It looks like Gatorade, but it doesn't taste like it. Anyway, so we're going to learn about that next week. Okay. Poof. All right. I'm done with that. Any questions? I'll end the video. That one kid that tries to drink it. Yep.